So we are the TriRobot group. We are working on the traversal of the cable and deployment of a sensor packet or a robot down into a skylight. Our group is myself, Prannoy, Rick, and Jonathan. And we're getting mentorship from both the Steves, Huber and McGuire. Okay, so we're going to start off with a demonstration of our robot actually working. This was a field test done 2 Sundays ago in a quarry about 2.5 miles away. So here you can see our robot is carrying a sensor packet. It's traversing across a cable that was pre-set up. So on the top of our robot we have a motorized pulley system that allows it to traverse. It has an encoder on it in order to keep track of its location. Let's see. And then you can see the sensor packet hanging below. Our cable management system, the ferret is currently disconnected from it, but you can see how the cable comes out and then is held in place with a weight. So here's the ferret lowering down. I guess it's hard to see with the robot on this, but there's a winch underneath here that the wire sends across, and it's anchored on the other end, and there's a connection for the ferret.
Ferret is the sensor package, but
yeah, I got it. Okay, so motivations for the project. So we want to explore these skylights, and in order to explore them, we have to be able to get inside of them. So the other rigging group is working on getting the cable across the skylight. We need a way to traverse it and then descend into the skylight. So the reasons we want to do this, it's unexplored territory. We haven't been able to get down there before. And these lava tubes that the skylight is formed from pose as a great place to possibly shelter human life in the future. They provide protection from asteroid and radiation bombardment. Also, we're competing in the Google Lunar X Fund. There's chances to gain additional funding from exploring these skylights. So for that video that we just saw, this is the quarry that we did our testing in. So in this quarry, with our sensor packet, we were able to map the walls of this. So it was a successful demonstration.
Okay, so kind of like that slide showed, the overall mid-semester goal was to take this robot out with the sensor package and autonomously map the walls of the quarry. So we were divided, or it was like a lot of people working on this project. There's a team working on the controls and data processing, a team working on the electronics. Our main job was to get all the mechanical components working. When we joined the project team, the frame was already built. A previous test had been done where the whole trolley was just on these 2 pulleys, the cable was up and it was just kind of strung out on a rope, and it was pulled back and forth by hand, and some of the data was gained. What we needed to do to make this whole process autonomous, first thing was add this motor which drives the carriage across the cable. We also looked into making a servo-controlled counterbalance system. We'll talk about that a little more. We found out after the field test that that's probably not necessary. That was one thing that we researched into. We installed all the electronics. We designed this power delivery system, so as the ferret was lowered and raised, we'd still be able to get power down to it, control the sensors, read all the data we needed to, and save it on the onboard computer. And like we said, we tested these features first in the high bay, in New Simon, and then finally in the field. Okay, so now we're going to talk a little bit about the specifics of each of these systems that we designed. First, the drive assembly. We use a friction-based pulley system to drive on the steel cable. It has a wrap angle of about 270 degrees, and given 270 degrees and the high tension caused by a pretty tight cable and this robot, which weighs probably about 60 pounds, allows enough friction to drive back and forth across the cable like you saw in the video. The system drives about 20 feet per minute. We have an encoder installed right here that measures how far the robot traverses along the cable to allow you to know how far your whole sensor package is moved, because it's just straight down from the robot, and then you use that data to aid in your mapping. And with this system, it was accurate to about 6 inches over 20 feet. There's a little bit of slip though, because you're relying on friction to drive the whole system.
So this is the a scale model, as you can see over there, that we were worried about this entire sensor package swaying because of wind or just because of existing vibration and whatnot. So that was the cause for developing a scale model. So as you can see over here, the servo, there's some control electronics in the back, including accelerometer that senses the angle that the sensor package is at. And then there's that large aluminum block, which is actuated by the servo, and that serves to counterbalance the entire sensor package. So after field testing, we saw that most of the oscillation was inside the ferret, or the component of the robot that was lowered down into the pit. That was, because that was such a long pendulum, that was where most of the oscillation was. So we have some solutions that we're going to implement after this that will try to reduce this. But it was deemed unnecessary to have this type of active stabilization on the traversal part of the project. So this is the ferret. It is a long cylindrical package with a LiDAR camera and IMU, and it also has the retroreflecting prism, which is used for absolute position tracking for validation and whatnot. So this is lowered down by the winch over here. There's two pulleys, and then the cable goes through the two pulleys, and then that's lowered down. We also have an encoder over here. This is the wire that goes to the encoder that measures how many revolutions of this spool have taken place. The problem with that is that it doesn't give you an accurate position measurement because the cable wraps differently every time around itself on the spool. So we have a potential solution for that that we're going to talk about later on.
So next we actually have a video of what the ferret was capturing. If I can play that. And as you see, just as like Pranay was mentioning, there's a lot of wobbling that's going on in the ferret, and that's due to, I guess, the current design of it. And that's something that we are going to be working on in the future. We also, one of the other things that we were able to do was install the necessary electronics for the carriage and the, I guess not the ferret, because that was previously designed. We were able to install the PC rather, as well as all the batteries and everything. Thanks a lot to Steve's help, as well as the power delivery to the ferret. So for our main deliverables, the things that we're going to be working on in the future in order to improve our current design, we've developed the new tie robot. Essentially the strapping on mechanism to the cable, so that it's able to be quickly and easily, I guess, attached. Right now, the only way you can attach this is literally to have it pre-strung onto the cable, because there's no moving components, obviously. So what we're looking into doing is essentially having a more advanced system that's capable of gripping onto a pre-strung cable by itself. The metric of success that we determined for that system was that it should be able to do that within 1 minute autonomously, once it's positioned in the correct place with respect to the cable, or to the line.
The second deliverable is there was error, the 6 inches over 20 feet. That was the error in tracking the horizontal position, and we hope to rectify this error by trying to sense the color of the cable that is being strung across. So prior to the mission, the cable should be either painted or taped around. That's what we'll be looking into, with different colors that encode patterns on the cable, and these patterns encode absolute position. So you can get relative position from the encoder, but that will be corrected periodically through the absolute position from the color. And the way you detect color would be through this nifty sensor here. I can pass that around. It's in this bag. It's a sensor. Basically, there's a white LED on it. That LED sends a white light onto the rope that's reflected back. And there's 3 sensors actually within this chip, and red, green, and blue. And each of these produces a voltage that can be read by a microcontroller. And then based on that, you can determine the color of the rope up ahead of you. So in addition to this make it sort of mechanical design, we will be looking into like what kind of encoding schemes, how many colors do we need on the rope, and is it possible to read the same sequence forward and backwards and so on.
So, and our final major deliverable that we're hoping to have completed by May is to design a more contained and robust ferret lowering system, or any kind of package you determine to lower in the future. The way we have this, that we're planning on having this design work, is instead of having one spool like we have on here, we'll have two parallel spools at about 12 inches apart to give the ferret stability, swinging in the horizontal direction. And we're also planning on, currently we're using this really thin aircraft cable, and like we said, as it wraps around, you're not sure exactly how thick the wrap is, and therefore the encoder values are very inaccurate, because you could be letting out, you're letting out a slightly unknown amount of cable, and that error adds up over time. So with this design, we're planning on using this wider webbing that will wrap around each spool in only one single thickness layer, so you can come up with a pretty simple equation that will, based on where the current height of the ferret is, and you'll know the radius of the spool, and so you can easily tell using the encoder values how much of the webbing you're letting in and out. And like as I said earlier, because you're adding this extra stability by using two cables instead of one, it'll decrease the ferret oscillation enough to get useful data, or more useful data. A little bit of oscillation is okay because the IMU can account for that, but it builds up over time, and it's harder to make up for that error with more oscillation. So this should fix that problem. And then just kind of overall, the goal right now is we have this prototype done. It's kind of quick and dirty, as you can tell. It was really just to get something out there that we could show could work, show could collect data, and could accurately, and could move along this cable. But now, in order to have more proof of concept that this could work in space, and to get additional funding for it, we need to make a professional-looking product. And so that's kind of where all these things fall under systems for a professional product. And you guys can come look at this afterward, because we can pass it around if you want to see anything up close, but I think we're ready for questions.
Yeah.
You mentioned 60 pounds for the weight of the device. Is that the device we're looking at, the ferret